Okay, let's go ahead and get started. We have several topics to cover. The general theme of this week's homework is work and energy. Incorporated within that is a few different topics: kinetic energy, potential energy, and then also power. So I'm going to review the concepts sort of as we go through and talk about the different problems that you'll see as you're working through the homework. So we'll start with the first one. The first one is kind of an SAT problem. You've got a father and a son. You have a relationship between their kinetic energies. And then you're given a change in the father's speed, and you're asked to find our initial speeds for the father and for the son. So initially, he has a third of the kinetic energy of the son. So we'd say that K for the father initially is equal to 1/3 K for the son initially. And we're told the son has half the mass of the father. So you could say that the mass of the son is equal to half of the mass of the father. And then the father is going to speed up. And after he speeds up, they'll have the same kinetic energy. So the kinetic energy for the father finally will be equal to the kinetic energy for the son finally. And we're also told that the velocity of the father final is equal to the velocity of the father initial plus whatever speed he gains. So in my problem, it's 1.1. And this is our sort of a system of equations, right? We have 4 equations here and quite a few variables. One thing that we should mention right now is that the kinetic energy, the expression for it is a half mv squared. Hopefully you've seen this by this point in the week. So using that with our first equation, we could rewrite that as the, let's see, 1/2 the mass of the father times the velocity of the father initial squared is equal to a third the mass of the son times the velocity of the son initial squared. That should be, sorry, a third times a half. Let me take that again. 1/3 times a half mass of the sun, velocity of the sun initial squared. Okay. We can also rewrite our third equation here as 1/2 the mass of the father times the velocity of the father final squared is equal to 1/2 the mass of the sun times the velocity of the sun final squared. It should be an F there. Okay, and yeah, so we have these relationships, and then the other two here we can substitute in to these equations. Maybe substituting in for the first equation, the second relationship with about the masses. The mass of the son will be half the mass of the father. So we'll have 1/2 mass of the father, velocity of the father initial squared is equal to a third times a half. And then the mass of the son, we're going to substitute in 1/2 the mass, 1/2 the mass of the father. And then we have the velocity of the sun initially, that will be squared. Quite a bit going on here. What we'll get now, if we cancel out the mf, the mass of the father, we'll get a relationship about the initial velocities. So to bring, we can put this somewhere. Let's go ahead and put it down here. This tells us that 1/2 the velocity of the father initial squared is equal to a third times a half, which will be 1/12 the velocity of the sun initial squared. And that's a useful relationship because it has eliminated mass. We have a relationship with the velocities, which ultimately we need to find for our two answers here. This is an equation with two unknowns, so we need one more equation. And that's obviously going to come from our other kinetic energy relationship. The second equation, plugging in the mass relationship into the second equation here, we'll get that the, oh, actually, I mean, I suppose that we could solve, well, okay, let's go ahead and plug that in. Doing a similar substitution, I'm just going to skip just one step if everyone's cool with that. Doing a similar substitution here, we'll end up with 1/2 the velocity of the father final squared is equal to 1/4 the velocity of the son final squared. All right, so now we have two relationships with the velocities. The last thing we need to do then is get everything here in terms of the initial velocities, because we're ultimately trying to solve for the initial velocities. We have one equation here that will allow us to put the final velocity for the father in terms of the initial velocity for the father. The other thing we need is a relationship between the final velocity of the sun and the initial velocity of the sun. You'll notice that it doesn't make any mention anywhere here that the sun's velocity changes. So that relationship will just be that v final for the sun is equal to v initial for the sun. Then we'll go ahead and make those substitutions, and depending on what your change in speed is right here, that will determine what your solution ends up being. Nina, I'm not exactly sure which step is the last one. We are trying to find a relationship between the speeds here. So our goal is to generate relationships for the speeds. We have the two relationships for the kinetic energies. And we know that those will relate the speeds, but they also have mass information in them. So we use this guy right here to relate our masses and cancel our masses out of our kinetic energies relationships, and that will give us a relationship for the speeds. Okay. Yeah, so now you have these 1, 2, and then 3 and 4. So your next thing would be to substitute in the expressions for the initial velocities, to sub those into this bottom equation right here. And then you'll have a system of two equations, and I'll leave solving that up to y'all. Okay, oops. Our second problem here. Our second problem, you're going to see you'll have a displacement vector and a force vector, and you're going to be asked about the work. So work is a new concept. We'll relate it to energy in just a second, but what we need to know is that work is a scalar product of the force and the displacement, F dot D. If you remember the dot product from back at the beginning of the class, the dot product is also called the scalar product. It produces a scalar. So the force and the displacement are both vectors. Once we take a dot product of those two vectors, we get just a simple scalar. One thing I will note is that scalars do have positive and negative, and it is important to keep in mind what makes a work positive or negative. The short answer is, if the force and displacement point in the same direction, you'll have positive work. If the force and displacement point in opposite directions, you'll have a negative work. You're going to get tested on that quite a bit in the homework, so we'll talk about it as we go through some problems here. For this first problem, you're just asked straightforward to just calculate a displacement given two vectors. So you'll have a force vector that is some x component for the force I hat plus some y component for the force j hat, and you'll have a displacement vector that is some x component for the displacement I hat plus some y component for the displacement j hat. And the way you calculate the work, if we're going to do the dot product, the work is just the x's multiplied together. So f sub x, whoops, times d sub x plus dy multiplied together, f sub y times d sub y. Make sure that you keep track of your signs here. So for instance, if I had that, let's say my f is 3i hat minus 2j hat, and my d is 4i hat minus 6j hat. What that would look like when I go to calculate my work is that the force would be, the x component of the force is 3, the x component of the displacement is 4, I have plus the y component of this force. You'll notice there's a negative sign out in front, so that y component is -2, and the y component of the displacement would be -6. Ensure that you include your negatives, because as I mentioned, even though work is a scalar, so it doesn't have a direction, it does have positive and negative. That can be important. For this example problem here, we just happen to have 12 plus 12, which is 24. And the units for work will be joules, J. And a joule has a ton of different definitions. It can be a Newton meter. It can be a kilogram meter squared per second squared. It could be a kilogram meters per second squared, meter squared per second. Oh, that's the same units. Anyway, yeah, so that's one definition of work that you will be asked to use. The important thing here, though, I would say that the most important takeaway from this definition here is that positive work is when F and D are in the same direction. And a negative work means that F and D are in the opposite direction. The one other thing that I'll note that we'll see as we go into the next few problems is that you can find a work of individual forces, or you can find a network of all the forces put together. The first few problems we're going to do here, they're going to ask about the network. So the network, this is problem number 3. The network is equal to the net force dotted with the displacement. Why am I making this distinction? You remember that we've done quite a bit with net force and finding the net force and summing forces together to find the net force. So you're going to be responsible now in some of these problems with finding the net force itself by summing the forces in the x and y direction. And then last step will be to actually calculate the net work due to that net force. So for the first problem, you have a situation like this where you've got a box on a floor and you'll have 3 forces applied to it. The floor is frictionless, so these are the only forces that we have. We have an F1 to the left, and that's F3 downward, and an F2 at an angle. And if you're given an angle off of the horizontal for F2, and we want the network done by the 3 forces. So in other words, the network is the work done by the net force. And then we're going to talk about energy transfer. So first thing is, how do we find the net force here? The other forces that are involved in this problem that are not labeled are the normal force upward and the weight or the force of gravity downward. In order to find the net force, well, we know that this is going to move along a frictionless floor. So if it's moving along the floor, the net force will just come from summing the forces in the x direction. The only forces we have in the x direction we have our F2, the component of F2 that is in the x direction. So it'll be F2 cosine theta. And then in the negative x direction, we have F1. Now, what we've done, what we did last week especially, is we sum our forces, we set it equal to ma. If a is 0, we set it equal to 0. In this case, though, we're only going to be concerned with the actual net force itself. So this is the x component of the net force. If I wanted to find the y component of the net force, I would just sum the forces in the y direction. I have my normal force up plus the y component of force 2, which is F2 sine of theta. And then downward, I have the weight and I have F3. So minus, that looks like a minus sign there. That should not be a minus. Minus the weight minus all of F3. And again, last week, we'd set this equal to ma. If a is equal to 0, we set it equal to 0. This week, we're actually just trying to find that net force. And you'd plug in whatever numbers you have in your problem, and you'd find the net force in the y direction. So now that we have our x component and our y component of the net force, we just need to relate that back to our net work. And in order to do that, we still need our displacement vector. Well, the displacement vector will be given to you in the problem. They're saying it's moving, in my problem, it's moving to the left some distance. So my displacement vector, if it's moving to the left, would be negative, mine happens to be something like 2 meters, negative 2 meters in the I hat. Since it's not moving up or down, there is no j hat component. Yeah, Lauren, so these things are equal to ma. However, what you're actually trying to find here is like ma, the net force. So that's why it's not written down in this equation, because we're actually trying to find the expression for the net force. Okay, so last thing is, now that I have, so now that I have my two vectors here, I have my x and y component for the net force, and I have my x and y component essentially for the displacement. Now I can calculate the net work, and we know that our net work will be the dot product of the net force with the displacement. So what that means is we'll have the x component of the net force times the x component of the displacement plus the y component of the net force times the y component of the displacement. Now here's something that I kind of alluded to, but which I haven't explicitly stated. You'll notice that our displacement is all in the x direction. It's all I hat component. That means that the y component of the displacement will be 0. It's all x displacement. There is no y displacement. And so that means that the term, this second term here, and this dot product is going to be equal to 0, because 0 times the net force in the y direction is just 0. So this will go to 0 actually, and we'll just have that our net work will just be the x component of the net force times the displacement in the x direction. Obviously, I'll leave the calculation up to you, but this is where your x force will come from. Now, we know to find work. We know to find net force. That's good. F net does not go to 0, Lauren. The y component of the displacement is 0. So this is because d sub y is 0. So it's the product of those. Okay, cool. So we can find work by taking a dot product. What we ultimately will relate work back to is energy. So we have two relationships for these. They're often written in a line, but I'm going to write them kind of separately so I can talk about each of them. So we have work is equal to the change in kinetic energy And we also have that work is equal to the negative change in the potential energy. We talked about kinetic energy in the first problem. Yeah, we don't, Michael, we don't assume that there's no vertical displacement. They tell us that the displacement is leftward. So yeah, so that is included in the given information. You don't have to make an assumption there. Yeah, so and by the way, we're still on problem 3. So we talked about kinetic energy. Kinetic energy, remember, is a half mv squared. So I'll just write that down. So kinetic energy is related to the mass of an object. You have to have a mass to gain an energy. And it's also related to the speed of the object. If I do work, in other words, if I apply a force over a distance or over a displacement, if I do work on an object, I will give it kinetic energy. I will cause it to speed up. So this is sort of related to, if you want to conceptually kind of tie these things in our first few chapters, we had motion where you had an acceleration, that we related that acceleration to the force. What we're doing here is we're sort of taking all of that motion and acceleration of the force and folding it into the singular concept, which tells us that the work done over a displacement, the force applied over a displacement, will give you some speed, right? This is just motion all over, but it gives us a very shorthand sort of way of getting from a force to a speed, say, that's changed. And it makes sense that if I apply force, I'm giving an object an acceleration, I'm causing it to speed up, so it's gaining kinetic energy. So that's work gained, or rather energy gained. On the flip side, we have something called potential energy, which we haven't seen yet. There are a few different types of potential energies. The first one that we'll be concerned with is called gravitational potential energy. And just to give it an expression, one expression that you'll see for it is mgh. Remember, mg is a weight. H is the height above a ground. So potential energy says that if I hold my pen up here, my pen can fall a certain distance, unless it has the potential to gain all of that kinetic energy, right? So it's sort of imbalanced. If I were to drop it, that potential would transfer into kinetic energy. That's called the conservation of energy. But most importantly, when I do work on an object, I will cause the potential energy to decrease. So when my pen drops, that gravitational force is doing work and pulling the pen toward the ground. And as that gravitational force does that work, it's going to decrease the potential energy that could be gained until my object hits the ground. So in part B, they ask about a net transfer of energy. They ask, is it to or from? Well, in order to determine that, all you need to know is if the work is positive or negative. Positive work is a gained energy. Positive work means a positive change in the kinetic energy. And negative work means a negative change in kinetic energy or a loss of energy. And so that's how you'll answer part B and C. I'll leave that to you. But those concepts are going to be important, especially moving forward. For example, problem 4. We have a horizontal force applied to a book, and the book is moving up a frictionless ramp. And we need to find the net work done on the book. And then we're going to relate that to speed change. So first of all, we want to find net work. Net work is equal to the net force dotted with the displacement. If I want to find the net work, I need to find the net force. Our displacement can give us an idea, going back to this problem that we just looked at. Remember that because our displacement was only in the x direction, we really only needed to be concerned with the x component of the force. So when I have a block on an incline, like I do here, if I'm given a displacement that is parallel to the incline, that's my entire displacement right there. If I'm given a displacement parallel to the incline, then my net force, or the only component of the net force I need to be concerned with, is the net force that is also parallel to the incline, right? I just need to multiply those two together in order to find the work. So what are our forces parallel to the incline? We have that applied force, so we'll have some applied force that is parallel to the incline. Since that force is parallel to the ground, it'll be Fa cosine of theta. I sure wish. Okay, and then the other force, it's a frictionless ramp, so the only other force we need to be concerned with is the component of gravity parallel to the ramp, which we know is the weight times the sine of the angle theta. And so without concerning ourselves with all the other forces involved in this problem, we can say that since the net force is equal to the net work is equal to the net force out of the displacement, we could also say that this is just the component of the force, of the net force, just the x component, times the x component of the displacement. Where here we're saying that, our usual x is up the ramp and y is perpendicular to it. And so now, so now we're just going to find the net force in the x direction. We have our Fa cosine theta going up the ramp minus our weight sine of theta going down the ramp. And then we have the x component of the displacement, whatever that happens to be. That will just be given to you in the problem as the displacement along the incline. So the drawing here comes from the problem, which just, here's the drawing in the problem. They do this, and then they give you that this is the displacement. And to hopefully answer Michael's question as well, this F sub A is given as parallel to the ground. So this is not the weight is perpendicular to the ground, which means that, yes, Lauren MG, which means that if this is the angle theta, then if I want the component of the applied force parallel to the incline, it's the same theta there. So it's adjacent, so that'll be cosine, which is why this is Fa cosine theta. And then the weight parallel to the incline is always sine theta, always, 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 always. Okay. Part B, this problem is going to ask us to relate this net force, whatever, the network rather, to the change in kinetic energy. So we know that work is equal to, it is technically the network, which is related to the change in kinetic energy, which will be equal to K final minus K initial. They tell us in the problem explicitly that K initial is 0. So this will just be equal to 1/2 times mv final squared. This is how you'll relate whatever network you find here to the final speed. So rather than having to find a net force, turning that into an acceleration, and then doing some kinematic stuff, we can simply find the net work and set that equal to 1/2 mv squared. And that gives you a little bit of a quicker way of solving these problems. So I mentioned that gravitational potential energy is one form of energy. Another form of potential energy is spring potential energy. And for spring potential energy, the equation is just 1/2 times kx squared. K here is what is called the spring constant. It just tells you how stiff or loose your spring is. The stiffer the spring, the larger the spring constant. In other words, It'll be harder to stretch or compress your spring if it's very, very stiff. The x is the displacement from equilibrium. In this first problem, they set x equals 0 to the equilibrium. So luckily, they're going to sort of walk us through this problem with what's going on here. The one thing they don't give us is they do not give us k explicitly. All they tell us is that we pull our block out to some initial x, and we apply a force to get it there. So in order to turn that into a spring constant, we have to use our relationship between the work. If we want to relate a force to an energy, we have to, well, I'll actually just give you the other relationship because it's a little bit easier. This comes from the spring force. And the magnitude of the spring force, we could say, is equal to kx. It is x is also a vector, and there's a negative sign out in front, but someone's going to ask, why is that negative, and then where did the negative go? So we can just say that the magnitude of the spring force is equal to kx. Yeah, so for instance, for my problem, they tell me that the magnitude of the applied force is 360 newtons, and that doing that pulls us out to 5 centimeters, 0.05. And so 360 times 20 is 7,200. 7,200, and it'll be newtons per meter. Now, this isn't actually an answer in this problem, but you are going to need it in order to solve the rest of the problem. So I'd recommend finding that first. And then for each of these problems, what you want to do is you want to find the work the spring does on the block as the block moves from one location to another. So remember that work is equal to the negative change in potential energy, which is the negative potential final minus potential initial. If you'd like to distribute the negative sign over the parentheses, you get that this is U initial minus U final. U initial will be the same throughout A through D of this problem. It's always going to be a half times the K that you found times the X initial that they give you. They tell us that we're going to pull the block. For me, it's out to 11 centimeters and then release it. That'll be your initial X. So you'll calculate some half kx initial squared, and you'll use the same one every time, and then you'll just subtract out a half kx final squared. And they're going to give you different x finals. Your k, of course, will come from the force relationship right here, and then you'll just plug in your different x finals for each part. Lauren, that just came from my problem. My problem gave me the block is pulled. They're going to tell you the block's pulled out a certain distance and that it takes a certain force to get it there. So you have to relate this force to whatever distance that force is related to in the problem. Cool. And then the x initial does not change. The x initial is wherever the block is released from. So in my problem, they say pull the block to x equals 11 centimeters and then release it. So that's my x initial. That's going to be the same throughout the whole problem. The only thing you're going to change is x final. X final is whatever x they give you in A, B, C, and D. Okay. Yeah, cool. Okay, so work is force dotted with displacement. There's another definition of work that you technically need to be responsible for, which is if your force varies with the displacement, what do? Well, you actually, like mathematically, you have to do a dot product of the force with the displacement at every incremental displacement, and then you have to add those all up. And I'm saying it that way because hopefully that reminds some people of an integral, because that's what the definition is. So from work is equal to force dotted with displacement, we get this more complex definition that the work is equal to the integral from d initial to d final of the force as a function of x dotted with dx. And that's technically a vector too. Now, I'm giving you kind of a technical integral definition. The way that you're often going to be using this is something like integral from, actually, I think the only way that you'll use it, and at least in the homework, is it's the integral from x initial to x final of the function in terms of x times dx. So let's do an example here. Problem 6. I'm asked to find the work done on moving a particle from x equals 0 to some other x. And well, I know that that work will be equal to the integral from x initial to x final of my force in terms of x times dx. So that'll be the integral from x initial to x final. The force equation that I'm given is F naught times x on x naught minus 1 dx. Yeah, here's the last slide. It's the same. I wrote the same thing down on the next. Cool. Okay. All right. So we'll do an integral here in terms of x. Everything else there will be a constant. The first term, when I integrate it, well, I'll still have an f0, f naught out in front. Integral of the inside, integral of x on x naught will be increase the power by 1 divided by the new power. So that'll be x squared on 2x naught. And then I have minus the integral of 1 with respect to x. It's just x. And then I need to evaluate that from x initial to x final. This is an integral that I'm sure everyone is comfortable with. I suppose I'll just leave this here. You should be able to solve from here. You're given all the values for everything here. I'll leave the evaluation of the integral up to y'all. Okay. The next problem is going to ask us to calculate a power. So power has two definitions. The first one, which is just the average power, is that the average power is just the work done over some time interval. So in other words, if I can find the work done, which I've done plenty of, I have performed that calculation plenty of times so far, then I just divide by the time it takes to perform that work, and that will give me, the power required. So in a given problem here, we have an elevator with a certain mass. The elevator also has a counterweight. So to draw a picture here, here's your elevator. The way elevators work is you have a really big drum at the top, and on the other side is a counterweight. So this is the elevator, and this is a counterweight. And the counterweight is usually close to the weight of the elevator. The point there is that you don't want your motor to be in charge of fully lifting all the weight of the elevator. So instead, you place a counterweight on the other side, and then the motor just gives a little bit of energy in one direction or the other to determine whether the elevator goes up or down. So in this problem, let's say that we have like, 1,000 kilogram elevator and a 900 kilogram counterweight. then since the counterweight, since 900 kilograms from the counterweight cancels out 900 kilograms from the elevator, the drum at the top is only responsible for moving 100 kilograms instead of needing to move the entire 1,000 kilograms. So it's just less stress on your system. You do need a little bit more, and as far as the support on the drum goes to the ceiling, that's kind of the trade-off. But you're not going to need to design any elevators in this class. All right, so if I want to find the work done by the motor, and then I can relate it to the power of the motor. So the work done by the motor, so far we've only done net work, but if I just want the work done by a single force, I just say, instead of doing net work is net force times displacement, net work, or rather the work of the motor will be equal to the force of the motor dotted with the displacement. The motor, we are lifting our elevator upward. So the motor is applying a lifting force. So that'll be the F of the motor. And we know that it needs to lift the difference between these two weights. So the force of the motor will be the, let's call it the mass difference. Well, yeah, I'm not going to use delta. The mass difference times the gravity, mg, and then we just have times the displacement. Now, since this is a force upward and our displacement is upward as well, we can just say that this is just the displacement. And then as far as calculating the mass difference, it'll just be the mass of the elevator minus the mass of the counterweight. And then we just multiply this by G and by D. G is 9.8 and D is the distance that the elevator will be moved. Keep in mind, this is your work. Ultimately, we need to relate it to the power. So the last step will be to plug it in here. And we get the power is equal to the mass of the elevator minus the mass of the counterweight times G times D over the time interval that's given. Yeah, always, always, always convert to seconds. All right. Okay, so the next problem gives us a graph. And your graph's gonna look something like this. Yeah, so that's a good question. If the elevator moves downward, the work would be negative because the motor is always providing an upward force. So you'd have an upward force dotted with a downward displacement, which would give you negative work. Okay, so for our next problem, we have a plot that looks something like this. I should probably use different colors here. Not sure, I'm gonna mute you. Okay. And it's pretty square and even as far as like what the values are. It's like this is like 1, this is 2, and then it carries on out to 3, 4, 5. I'm just copying the picture that's in your homework, so no need to really copy this down unless you want to have 2 versions of it. Yeah, good work, Lauren. Yeah, so the units there are joules per second for power. The other unit for power is a watt, which is just a W, and a watt is equal to a joule per second. Okay, so yeah, so this is, I guess I should say this is a force. So you'll have some like Fs up here, and then you have a minus Fs down here. And yeah, we have a force applied as an object is undergoing through some displacement. And first thing we want to do is find the, we're given an initial velocity and we are asked to find the final kinetic energy. So in general, we know that we can relate the force and the kinetic energy via the work. Work is equal to change in kinetic energy. Molly, do you mind? Who are you barking at? Sorry, it's the dog. Okay, so our work, we know is force out of displacement. I've done it 100 times. Since I have a graph, and this is a good lesson for the exam as well, a graph problem should indicate to you that you want to do some sort of calculus. And this is why this plot is set up with such like easy triangles and rectangles, is because we're going to find an area. And so the work will be equal to the integral of f dx. And that integral will come from the area under the curve. And we'll relate that to k final minus k initial. So instead we could say that this is the area. We want to find, for part A, the kinetic energy at some location. So we're looking for kf, k final. And we're given an initial velocity, and I believe we're also given a mass. So we plug those in to 1/2 mv initial squared to find the initial kinetic energy. As far as the area that we need to find, for the first part, they want us to find the area out to, or the kinetic energy, I should say. They want us to find the kinetic energy at 3 meters. So that means that we want to find the area under the curve out to 3 meters. I overran there. Okay, that looks a little bit better. So that's the area that I'm after. One thing that you'll notice is that these two triangles are going to cancel out. So the only area that I need to calculate is this right here. And this area is just length times width. So the length will be negative f sub s. That's the distance up and down. And then the width is just 3 minus 2, which is just 1. So that is our area. That is also our network from 0 to 3. I can go over kind of the relationships between all these topics if you want. Yeah, I mean, if you need the actual conceptual relationships between them, your lectures and your textbooks are going to do a better job of the conceptual relationships. And here we're just kind of dealing with problem solving. So that would be my recommendation. Okay, so yeah, so we have our work is related to this area, and we found this area to be negative f sub s. And we know this is related to k final minus 1/2 mv initial squared. And ultimately, for part A, we just want to solve for k final. So we know that k final will be equal to adding over the 1/2 mv initial term to both sides, 1/2 mv initial squared minus f sub s. This is for part A. For part B, they're going to give you a final kinetic energy that you're targeting, and they're going to ask you to find the x value where that kinetic energy is reached. So in that case, no, f sub s comes from the problem price, so it's going to be on the diagram. It'll be given in the problem. It's some constant value that they give us. It is the net force. Sorry, I guess in case you're asking this question, it is the net force in this problem because it's the only force in this problem. It's a very conceptual problem that we're dealing with. what was I saying? Yeah, so for the second part, we're given a final kinetic energy that we're aiming for. And instead, we need to solve for a displacement that final energy, that final kinetic energy is reached. So what you do is you'd start from, oops, you would start from this guy here. I just erased my final, I think. You'd start from this relationship, and in this case, you're actually going to solve for the area. So you'll get that the area is equal to some number, given your final kinetic energy. And then we need to relate the area back to the picture in some way. As I mentioned, these two triangles are still going to cancel out. So the area will be equal to just length times width. The length will be negative f sub s. And then the width will be x final minus 2. And the reason for that is because we're starting our rectangle at 2. So once you plug in your final kinetic energy and your mass and your initial velocity to find the area, you can relate your area back to the diagram using a relationship like this. And then the last question is going to ask about the max kinetic energy. So the first question that I would ask you as a sort of conceptual review, when you're trying to figure out what the maximum kinetic energy is, I would ask, where does it experience a max kinetic energy on this diagram? You start off, your object starts off at this point up here, and it has some positive kinetic energy. It has a mass, it has a velocity. As it moves from x equals 0 to x equals 1, this is still in the positive force side, which means that the work here is still positive. So right here, we are adding kinetic energy. Whoops. I try that again. Adding kinetic energy. Once the force flips and is now a negative force, then from here all the way out, we'll be subtracting kinetic energy. So if you want to find where the object is at a maximum kinetic energy, well, if it would be when it's just finished the gaining process. So it would be right here at x equals 1. And just as a little bit of a hint, you know your initial kinetic energy, and you're asked to find the maximum kinetic. So you're again looking for kinetic final, and you need to relate it back to an area. Well, the area will just be the area of this triangle right in here. So that'll just be 1/2 times the base, which is 1, times the height, which is f sub s. Okay. So the last two problems here are going to be, obviously, as you maybe picked up on at this point in the semester, these will be the most challenging, sort of putting all of our topics together to try and work through these last two. So the first one, and this is one that does creep up on exams from time to time. So I would spend some time with this problem to understand what's going on. You have a vertical spring, and the block will be dropped on this vertical spring. And let me draw this diagram. You have a block moving downward with some speed, and then you have a spring that's attached to the floor. And so let's talk about physically what's going on with this block as it moves through its motion. So I drop it from a height, and it's going to be in free fall until it hits a spring. And as it's doing that, it's going to be gaining speed. It'll have some potential energy due to gravity that's transitioning into kinetic energy as it gains more speed. Once it hits the spring, then the spring will compress. So at some later time, you'll have a compressed spring, and the block will have pushed on the spring. Now there's a height difference here as well. So that height distance will also be related to a change in that potential energy. However, the spring itself will then store kinetic energy. So you have a subtraction, of a potential energy due to gravity, and you have an addition of some potential energy due to the spring as that spring is compressing. Also, as the spring is compressing, it's going to be slowing down the block, and so you'd also have some decrease in the kinetic energy as the spring compresses. Now, ultimately, they're going to sort of walk us through this, but this is an overall view of the actual physics of the energy as it's being transitioned from one form to another during this problem. So the first thing that they ask us is, let's see, we have our block, we have K, which is a spring constant, and we also have the maximum compression distance. First thing they ask us to do is to find the work done on the block by the gravitational force. So in order to find the work done by gravity, I need to do the force of gravity dotted with the displacement. Hopefully we don't need to write out these quantities and solve them. We just need to think about the direction of our force and the direction of our displacement. Gravity is downward, and as the spring is being compressed here, my displacement vector will also be downward. So this will just be mg times whatever that displacement downward is, as given in your problem. If I want to find the work done by the spring, that will just be the force, you could say the force of the spring dotted with the displacement. Or we can say, the work of the spring will be related to the negative change in the potential energy of the spring, just negative U final minus U initial, which is U initial minus U final. Since the spring is initially just allowed to be stretched out, that means that your initial spring potential energy will be 0. And so the work done by the spring is just negative U final. They ask us to find next the speed of the block just before it hits the spring. So let's think about the physics, or the energies rather, that we have just before we hit the spring. At that point, we have just a kinetic energy. The spring has no potential energy. So I just said that the initial spring potential energy is 0. We have all kinetic energy, in other words. In this final picture, once the spring has fully compressed, our kinetic energy is actually going to be equal to 0 if it comes all the way to rest, as it tells us in the problem. So what that means is that our kinetic energy that we had here all went into spring potential energy in the compressed picture sometime later. Now we also have a loss of the gravitational potential energy, and that gravitational potential energy will also need to go into the spring. So in other words, our spring potential, call that final, will be equal to our kinetic initial plus the gravitational initial. In other words, the kinetic and potential that we lose as the spring compresses must go into the potential of the spring. That energy, in other words, must be stored in the potential energy of the spring. So if we want to find the speed of the block, obviously we want to relate that to kinetic energy. Maybe that's not obvious, but just remember that kinetic energy is a half mv squared. And we've found now our potential energy final, or we know it. And we can also, and we've also found, I guess, the gravity right here. So rearranging this equation, we'll have that our initial kinetic energy is equal to whatever our initial gravity is, and then minus, no, let me get these signs right. The kinetic initial will be equal to our spring potential final minus our gravitational potential initial. And then we can relate that back to 1/2 mv squared. In order to find each of these terms, remember that I'm sort of out of room here, but the potential energy of the spring final will be 1/2 kx final squared. And the potential energy due to gravity will be mgh. But h is also the compression distance x final. So you'll have the same x final, and in both cases, that x final will be equal to the displacement that's given in the problem. All right. One more. This problem has a pulley, and there's some physics involved in a pulley. I'm just going to talk a little bit about the physics of the pulley and what happens there to hopefully give you a chance to solve this problem as well. For this problem, we have a series of pulleys. So you have one that's attached to the roof, and then we also have a free floating pulley with a weight attached to it. And the rope is going to be strung like this and tied to the roof. And then there's an applied force. Let me make that a better arrow. So there's some applied force downward. They've got a hand in their diagram. And this force is applied force. Another way of looking at this is a tension. So there's a tension applied to the rope. And since tension is constant throughout the rope, since we can say that this force will transfer throughout the entire rope. And that's important to us because when we look at the weight on the other side, that weight has the rope pulling up on both sides of its pulley. So you'd have the force on the left and the force on the right. This is the mechanism by which a pulley serves to decrease the force necessary to move an object. In terms of the work and the energy, it means that in order to apply the same work, we have to apply a smaller force over a greater distance. But this is why a pulley is one of our simple machines. It makes doing work on this hanging mass easier because it requires less force. So if I want to find the magnitude of my force in terms of the weight of the object, I know that I'm going to be in equilibrium over here. I know that my hanging mass will be in equilibrium. And the forces on that pulley are that we have the two applied forces upward, and then we have the weight of the object downward. And again, I'm in equilibrium, so that's equal to 0. Another way of putting this is that 2 times the applied force is equal to the weight. Another way of putting it is that my applied force, since I'm using a free pulley, my applied force is only half of the weight, which is here mg on 2. So I have my force applied, and they asked what the magnitude of the force is to lift at the constant speed. Here you go right here, just mg on 2. The second part says we want to lift the canister 3.3 centimeters. How far must we pull the free end of the cord? Here's where the catch comes in. We only need to apply a force that's equal to a half the weight. However, because we know that the work applied has to be equal to the negative change in the potential energy. And since this is equal to the negative of mgh final minus mgh initial, which is the opposite of mg times delta h. Since our applied force must be equal and opposite to the weight times delta h, or rather since our work must be, we know that our work, remember, is F dot D. And so our applied force is mg on 2. We must apply that force over a distance d. Notice mg cancels out of both sides, and what we get is that d is equal to the opposite of 2 times delta h. What this tells us is that the distance that our applied force must be applied is, first of all, in the opposite direction of the motion of the canister, which is good. That's what the negative sign tells us. But it also must be twice the change in the height for the canister. And then the last two parts here are going to ask about the work done by specific forces. Yeah, let me take it one more time, Olivia. I have that you asked because I'd like another chance at explaining this. Whenever I apply a force to a rope, I'm creating a tension within that rope. So in this case, I'm applying this F force. Just think of it as a tension if you want. That tension will carry throughout the problem. So up here, there's a tension pulling downward because there's a rope there, and there's a tension pulling downward. And since those two tensions are pulling down on the pulley, that's like the force downward on that fixed pulley. There would have to be some force upward that's equal to two tensions that's supporting the weight of the pulley. Everything has to be in equilibrium. Down here, we have two sides, a tension and a tension, because there's two sides of the rope that are applied to this pulley. And acting downward is the weight of our hanging mass, which is mg. So these two tensions together support the mass mg. That's the whole point of having the rope slung around your moving pulley. And that allows us to find that the applied force, which is F, right? But this is just the tension, that the applied force is a half of the weight of the hanging object. Yeah, delta U that's just change in potential energy. This is just a fundamental relationship between work and potential energy. That your net work is equal to the negative change in potential energy. And then we know that we're dealing with potential energy due to gravity, which is how we then go ahead and plug in. This would be, I maybe skipped a step here. This is U final minus U initial. And then there's the negative sign out in front. Yeah, so U final is mgh final because it's a gravitational potential energy is mgh. And U initial is mgh initial because, again, gravitational potential energy is mgh. Cool. The last two parts are going to ask you to find the work done by your force and by the gravitational force. And there's sort of, you could get through this conceptually if you want. There's going to be a relationship between these two works. One observation that I'll make is that since our speed is constant, since the speed is constant, the change in the kinetic energy, one fear step. Since the speed is constant, that means that our K final will be equal to K initial. In other words, the kinetic energy won't change because that's 1/2 mv squared. If V doesn't change, kinetic energy doesn't change. And if the kinetic energy doesn't change, then our delta K is 0. And the reason that that's important is for the same reason that we can relate the net work to the change in potential energy. The net work, if the kinetic energy is 0, then the net work will be 0. Now, in part C and D, they're not asking for the net work. They're asking for the work done by these two forces, one of which is your applied force. Well, we know our applied force explicitly, and we know that that force is lifting the canister upward. So the work done by the applied force will be equal to the applied force times whatever that delta H is, the height difference. And since our net work is equal to 0, we could say that the work done by gravity will just be equal to the opposite of the work done by the applied force. They must cancel out. So that's sort of a shortcut. If you don't want to do that, you could say that the work done by gravity is equal to the force of gravity dotted with the displacement. And our force of gravity is mg downward while the displacement is upward. So that would be negative mg times delta H. All right, two different ways of solving that. But the conceptual relationship, I would say, is probably the most important thing, especially as you move forward. Okay, so that's the run through. I'm gonna go ahead and stop the recording here. If you have any questions, feel free to stick around.
Could you re-go over